guys, it's your favorite teacher, Godson, and this is Wits Learning Made Easy. As I said, for now, whenever see this video before, wanna they try to subscribe. In English, please, as much as possible, if you have never been to my YouTube channel before, and this is your first time, please try to subscribe. Now, like the videos too, and put on the notifications so that you can get the videos as they are popping out. Thank you. Okay, now in the other video we talked about redox. Today we're going to be talking about another part of redox reaction, which is rules for determining oxidation number. Now, we said earlier on that reduction and oxidation are defined in terms of increase in oxidation number and decrease in oxidation number. That means that we need to understand what oxidation number is and then find a way around how to determine those things. Okay, so what's an oxidation number? Generally speaking, the basic thing you could take as an oxidation number for is oxidation number is defined as the charge possessed by a substance. The charge possessed by a substance. So whenever you are looking into the charge of a substance, more or less, yes, the charge of a substance, you are looking at its oxidation number. Now, with that said, we are going to be considering about 8 rules which would help us find the oxidation number of elements in different compounds. With that said, let's get to it. The first rule in determining oxidation number is this: the oxidation number of a neutral element, substance, compound is always equals 0. I put it down. The oxidation number of neutral substances is always equals 0. So whenever you see a substance and you notice that that substance is neutral, it means that the oxidation number is 0. Now, before I continue on this lane, I would just like to establish a factor. Now, whenever you see a chemical symbol, every chemical symbol gives 4 pieces of information. Every chemical symbol, take for instance, we have X. You have 4 pieces of information that is going to be given by this chemical symbol. The first piece of information, okay, let me put it down here so it could be a little bit bigger. So we have the first piece of information that is given is the atomic number, written as a subscript towards the left. The atomic number will tell you the number of protons, which is a subparticle of an atom. So if you see an atomic number of 7, you see something like Cl17. It implies that the atomic number of chlorine is 17. Quite easy, right? Good. So the next piece of information is the atomic mass, which is written as a superscript towards the left. The atomic mass, we'll discuss this in other videos, but just have this in mind, that the atomic mass is given as the sum of the protons and neutrons. The sum of protons and neutrons will tell you about the atomic mass. Then the next piece of information that is given is the charge, written as a superscript I meant to say, towards the right, and then finally atomicity. Now, the place of emphasis in this particular symbol with respect to what we are discussing is the charge. So if you want to identify the charge, you are looking at the superscript towards the right. Once you notice that whatever value you have there is referred to as the charge of that element or substance or compound. So let's move ahead of that. Now, why did I have to mention this? I had to mention this because take for instance, we have a rule: the oxidation number of neutral substances is always equals 0. What does this mean? It means that if I have a substance, let's say I have sodium Na, and I have 11, and I have 23, and then here I have plus, and I have another sodium Na 11, 23, and nothing is there. Now, this is sodium ion because it is charged. Whenever you see a value, a numerical value attached to the superscript towards the right, it implies that it's an ion, a charged particle. But once you don't have any value here, it implies that it is neutral. So how do you identify neutral substances? Because that could be the question that could pop up. Yeah, we know oxidation number of neutral substances is equal to 0. Yeah, we know that. But how am I supposed to know that it's neutral? From the symbol. Once you look at the symbol and you notice that the superscript towards the right has no value, the implication of the statement is that you have a neutral substance. So How do you identify neutral substances? Neutral substances have the charges. They have no charges when they are represented in their symbol. So if I have something like H2O, and you notice that I don't have any charge here, is H2O neutral? Yes. So what is the oxidation number of H2O? It is equals 0. I have Na and I have no charge here, and because there is no charge here, the implication is that the oxidation number is also equals 0. Quite simple. Rule number 1, take note of that. The oxidation number of neutral substances is always equals 0. Okay, we move to the next rule. We're going to take them one by one and probably solve as many questions I might say, as possible to help us imbibe what we are learning. Okay, now the second rule is quite simple, and this rule has to do with charged particles, ions. I might not have mentioned this, but have this in mind. Ions are referred to as charged particles. So once you notice that on the charge area there's a numerical value, I told you guys that every symbol has the atomic number, the atomic mass, the charge. Once there's a numerical value here, it means that it is an ion. So have this in mind. The rule number 2 states that the oxidation number of a charged particle, or you could call it ion, is equals its charge. So what does this mean? If I have a particular charged particle, Na+, and I'm asked, what is the oxidation number of Na+? Please, you don't have to worry yourself. It's as easy as anything. What is it trying to say? Oxidation number of a charged particle is the same thing as this charge. So if Na+ has a charge of +1, the oxidation number is 1. Hope this is understood. Okay, imagine we have something like, let's say, CO3, 2 minus. Now, note this about oxidation number. If you represent charges, you write the numerical value before the sign. But when you want to show them as oxidation number, you simply intertwine them. So if you have the charge as 2 minus, the oxidation number is equal to the charge, but this time around it will be minus 2. Quite simple, right? Very easy. So have this in mind, that if you are dealing with a charged particle, the oxidation number of a charged particle, which is an ion, is equals its charge. Very simple. Okay, so with that said, we'll go to the third rule. The third rule is also as easy as the first and the second. And what is it trying to say? What is it trying to say? Now, the third rule has to do with a specific element, and that element is hydrogen. Now, whenever hydrogen is found in the compound, just have this in mind, that its oxidation number is always equals +1. I take it again. If hydrogen is found in a compound, its oxidation number is always equals +1. Yes, but there is an exception though. The exception is when hydrogen is found in a metallic hydride. A metallic hydride is a compound that contains a metal and hydrogen. So anywhere you see hydrogen, it should be +1 when it is in a compound. So if I am to ask you, I have a compound H2SO4, and I ask what is the oxidation number of hydrogen inside this compound. Obviously, because hydrogen everywhere is +1, hydrogen here also is equals +1. That's the oxidation number. However, there is an exception. The exception is when hydrogen is found in what we call a metallic hydride. Look at the name, metallic hydride. It means a metal combined with hydrogen. Yes, so we have sodium hydride. Sodium hydride in this case would have hydrogen with the oxidation number of -1. Why? It is combining with a metal. So have this in mind, that whenever you are dealing with your metallic hydrides, oxidation number of hydrogen is -1. But if you see hydrogen in any other compound, hydrogen is equals what? +1. Now note this too, that if hydrogen combines with metalloids like boron, for instance, in borane, BH, the oxidation number, H3 I meant to say, the oxidation number of hydrogen here is -1. So when you're dealing with metals or metalloids, same thing, the oxidation number of hydrogen remains -1. Okay, so I guess we are going to the next rule. So wherever you see hydrogen in a compound, just note that it should be +1. The only time it changes to -1 is when hydrogen is combined with a metal or a metalloid in a compound. Thank you very much. Let's move ahead into rule number 4. Now, rule number 4, just like hydrogen, has that anytime you see oxygen found in a compound, if oxygen is found in the compound, the oxidation number of oxygen is always -2 when it is found in a compound. I take it again. The oxidation number of oxygen is always -2 when it is found in a compound. The implication of this statement is that if I have H2O and I'm asked to find the oxidation number of oxygen, I don't need to solve anything. All I need to know is this rule, which says that anywhere I see oxygen in a compound, the oxidation number of oxygen is -2. There is only one exception. Okay, there could be more than one, but there is a major exception for our curriculum. And that exception is when oxygen is found in what we call peroxides. Peroxides. What do I mean by peroxides? For instance, when a metallic oxide has one extra oxygen or one more oxygen added to it, it forms a peroxide. I take it again. Imagine you have a metallic oxide of sodium, which is Na2O. The peroxide of sodium is formed when you add one extra oxygen. So every peroxide has one extra oxygen or one more oxygen than its corresponding metallic oxide. So have this in mind. If you have Na2O as the normal oxide of sodium, the peroxide is Na2O2. So have this in mind. Here, oxygen is found in a normal compound, so the oxidation number of oxygen here is -2. But once you see it in a peroxide, it has changed. Where is it gonna be? -1. Have this in mind. I take it again. The oxygen found in any compound, anywhere, metallic, anywhere at all in the whole wide world, it should be -2. But there are certain exceptions. One of them being when oxygen is found in a peroxide. If oxygen is found in a peroxide, its oxidation number is -1. Its oxidation number is -1. The other exception is when oxygen is found in a compound known as oxyfluoride. In oxyfluoride, the oxidation number of oxygen is +2. However, as I said, for most of the compounds you're going to be looking into, especially in your secondary school, you would have oxidation number of oxygen as -2. Everywhere you find oxygen in a compound, it should be -2. The only exception is when oxygen is found in a peroxide or in an oxyfluoride, where it becomes -1 in the peroxide or +2 in the oxyfluoride. Thank you very much. I hope we're following this. That means if I have something like let's say NO2, the oxidation number of oxygen here is no. What is it going to be? -2. So have that in mind that anywhere you see oxygen in a compound is always -2, and that's the vibe for now. So we move ahead. Move ahead with the rules. I told you that we are gonna be looking into about 7 thereabout rules, and then that will be that for today's video on that. Okay, we go to the next rule. Rule number 5. This rule is a very important rule, and for you to understand this rule, you need to have a little bit of understanding of the periodic table. First of all, is the periodic table is segmented into 18 columns and about 7 rows. Out of the 18 columns, you have what we call the main group elements. The main group elements are from group 1 to group 8, and the rest of them are found in between group 2 and group 3, and that's where you find your transition metals and all whatnot. However, we're not talking about the periodic table today. My point is this: the oxidation number of a main group element, when it is found in a compound, corresponds to its group. I take it again. The oxidation number of a main group metal, specifically the metals, the oxidation number of a main group metal when found in a compound corresponds to its group. So the implication is, if I know the group of my main group metals, I have the oxidation numbers whenever they are found in a compound. I don't mean when they are alone. No. Look, the oxidation number of potassium here is 0 because it's neutral. But when I have potassium in K2SO4, now, what is the group of potassium? The group of potassium is +1. Not +1. Is 1. So that implies that the oxidation number has to correspond. What will it now become? +1. So have this in mind. Have this in mind that the oxidation number of a main group element, the oxidation number of a main group element, the oxidation number of a main group element must metal, specifically the oxidation number of a main group metal, should correspond to its group in the periodic table. So if I have aluminium found in a compound, if I have aluminium found in a compound, the oxidation number of aluminium automatically, because I know it's in group 3, is equals plus 3. If I have something like lithium, lithium is plus 1. Sodium in a compound is going to be plus 1, and so on and so forth. So just have that in mind. Then we go to the next rule, which is rule number 6. What is rule number 6 trying to tell us? Rule number 6 is simply trying to say, number 6, the sixth rule is this, that if you have the algebraic sum of oxidation numbers of individual elements in a neutral compound, the algebraic sum of oxidation numbers of individual elements in a neutral compound is equals 0. What do I mean? I have a neutral compound, Na2SO4. How do I know this is neutral? I told us before that whenever you see a chemical symbol and you don't see any value here, this is where the charge is written. If there is no value here, it means that it's neutral. So the point is this: Na2SO4, no charge, meaning that it's neutral. Hence, what does this imply? According to our sixth rule, if we are to add sodium, which we have 2 of them, the oxidation number of sodium to the oxidation number of sulfur to that of oxygen, because it is neutral, the algebraic sum would give us 0. So have this in mind, that the algebraic sum of oxidation numbers of individual elements in a neutral compound will always give us 0. So have that in mind. Okay, we could actually try this out to see. For instance, this is sodium tetraoxosulfate 6, meaning that sodium, let's go back to rule number 5. Sodium is found in a compound here, and it is a group 1 element. Metal is a group 1 metal, meaning that the oxidation number is plus 1. But there are 2 of them, so times 2. If you listen to the name of this compound, I said sodium tetraoxosulfate 6, meaning that the oxidation number of sulfur is 6. So we have sulfur 6. Then oxygen is always minus 2 everywhere. The only exception is when oxygen is found in a peroxide. Having said that, we have minus 2 times 4. Let's see if this is going to give us 0. First of all, 1 times 2 is 2 plus 6 minus 2 times 4 is minus 8, and that is equals what? 2 plus 6 is going to give us 8 minus 8, which is equals 0. So we're proving that theory, that the algebraic sum of oxidation numbers of individual elements in a neutral compound is always equals 0. So have that in mind. Let it not confuse you. Then we go to the last rule, the final rule. What is the final rule? The final rule has to do with the charges, and it's saying that the algebraic sum, it's similar to the 6th rule, but then it's slightly different. The 6th rule has to do with neutral compounds. The final rule has to do with the charged particle. So let's get to work. Now listen, it's trying to say this, that the algebraic sum of the oxidation numbers of individual elements in a radical. A radical is a group of atoms which usually possess a charge. I'll take it again. A radical is a group of atoms which usually possess a charge. So have this in mind, that whenever I talk about a radical, I'm looking at a group of atoms, something like CO3, different atoms, and they possess a charge. So what do I call this? Radical. Okay, so the rule for the radical is this, that the algebraic sum of the oxidation numbers of individual elements in a radical is equal to the charge they carry. So let's take this. You have CO3 2 minus is a radical. If I'm to add the individual oxidation numbers of the constituent elements, it will give me the charge. So we have C plus O times 3. It should be equals, what is the charge here? Minus 2. And that's that. Now, let's see if this is going to work. Now, this is trioxocarbonate 4 ion. Trioxocarbonate 4 ion, meaning that carbon has the oxidation number of 4. Oxygen has the oxidation number of minus 2, which we know because oxygen is always minus 2 when it is found in a compound, except when it's found in the peroxide, where it becomes minus 1. So minus 2 times 3 equals what? Let's see if it's going to give us minus 2. So let's go. 4 over here. Minus 2 times 3 is going to give us minus 6. And 4 minus 6 is obviously going to be minus 2. So the rule is proven. So have this in mind, that once you follow these 7 rules, I'll put them right there so you can see them and have that. these 7 rules right here, you would have that you can be able to solve questions with respect to oxidation number. Now, we are going to solve some questions and find the oxidation numbers of elements inside compounds and radicals just to end the video, so that we could also go out and try out other examples. For instance, let's find, haven't noted the rule, let's find the oxidation number. We have MnO4 minus, and we are asked to find the oxidation number of manganese. Find the oxidation number of manganese in MnO4 minus. This is going to be quite simple. How do we solve it? Very, very easy. Now, what rule will apply here? The 7th rule, because this is a radical. And if we are going to be applying the 7th rule, it says that the sum of individual oxidation numbers of elements in a radical is equal to the charge they carry. So if I have Mn plus oxygen, there are 4 oxygen atoms here times 4. That's why I'm multiplying by 4. I'm adding everything. It's the same thing as saying Mn plus oxygen plus oxygen plus oxygen plus, yeah, but we ain't doing that. So just have that in mind. There are 4 oxygen. That's why oxygen multiplied by 4 is going to be equals the charge it carries. In this case, minus 1. So what do we have? Mn plus oxygen is minus 2 times 4 equals minus 1. Manganese is going to be equals, okay, so let's do this. This is minus 2 times 4 is going to give us plus minus 8, which is equals minus 1. Your mathematics teacher would have taught you this, that Mn minus 8 is going to be equals minus 1. Therefore, Mn is going to be equals minus 1 plus 8, and the oxidation number of Mn is plus 7. So all you need to do is apply your algebraic rules here. We apply the rule of oxidation, which says that adding the individual elements will give us the charge for a radical. We have Mn plus O times 2 equals minus 1. We are looking for the oxidation number of Mn. Oxygen is always minus 2 times 4. You do this and then your answer is given. I'll give you 2 examples to try out on your own and see if you are going to get them. They are going to be, find the oxidation number Cr2O72 minus. You are looking for the oxidation number of chromium, and if you have to solve it and get it correctly, your answer should be plus 6. So try that out. And then secondly, C2O3 2 minus, not O3, C2O4 2 minus. Your answer here should be plus 3. So try solving it and see if you're gonna get this. Thank you very much for watching this video. This is Wits Lounge, learning made easy.